mass moment of inertia, which in school you will have already covered area, and so when we get to mass, you're kind of already been vaccinated there. But I'm going to have to do it in reverse here to try to give you again some feeling for things. This concept of moment of inertia of an area. The term inertia first is a strange term. We think of something has inertia, which means it has some kind of potential energy or some built-in kind of thing here. It does seem strange. What I've shown here is a flywheel, a solid disc flywheel that's rotating around, and as it's rotating, it has some built-up inertia, and if you got it up to speed and you let it go, and the bearings that it's sitting on, are fairly frictionless, low friction, that thing will sit there and turn and turn and turn, turn for a very long time. But as you would know, is that the thicker this flywheel is, the more it will take to get it up to speed, or the bigger diameter it is, the more energy it would take to get it up to speed. You know that, okay? I mean, from just natural things that in your life, you kind of know that heavier or bigger or whatever takes more energy or has more, in a way, more inertia. And and we use the symbol for inertia. The first letter in inertia is I, so this is really a capital I. Unfortunately, it's in this Arial format of font, and so it's just a single line. But as you see underneath your notes there, it says mass. The inertia, mass moment inertia, is really mass at a distance squared, and that can be shown to be the case. This is the first level of quantifying this. It's not mass times a distance. It's not, how much do you have away from the axis. It's how much do you have away from the axis times that distance squared. So as we're going to see here shortly, two things that are the same whatever, but one is at some distance d, the contribution to the same thing at 2d is 4 times 2 squared, 4 times that particular quantity. So the farther you are away from the axis, and for us, the farther away you are from the centroid, the more contribution the moment of this area will have in the problem. And again, we're going to talk about how it feels here. So the key here in this particular expression is, even just for a flywheel or whatever, is this, the mass of it. And remember, mass back from physics is weight divided by gravity. So if you knew the weight of this, you divide by gravity, that'll tell you the mass. And then how far you are out, distance squared here. Okay, so the parts, what it says here means the parts of the object farthest away from the axis of rotation contribute more to the inertia than parts close to the axis. Okay. So that's what this means. Okay? So where it's located, okay, matters. Okay, and again, in your life, you are very familiar with this concept. You just haven't been able. You've never had to quantify it before, and that's what we're going to do here. Okay. Now I can take this solid disc flywheel. That basically is what you have at the back of the engine of your car, is a solid disc, either a torque converters on it or the clutch plate or something like that. But the flywheel you have, make sure your engine kind of keeps a constant revolution, even though your 8-cylinder, 6-cylinder, 4-cylinder is firing at odd times. The flywheel evens all that out. If you didn't have the flywheel, your car would shake itself. You would be like scrambled eggs before you got through there. So you need the flywheel to smooth out all of that. Well, some flywheels you see these in the old steam engines and whatever it is, big old flywheels. Well, if you had a big old piece of steel like this, man, you'd have something really, really big. Well, what you can do is you can create a flywheel by putting, based on that, the material that's close to the axis doesn't count. It doesn't count much. Get it out. Okay, so what you do is you come out here and you put a big old rim, and you put some spokes to connect the rim to the axle. And now this is can have the same thing. It's still area. Well, this is getting into the area, but what happens is this is considerably weighs less. I don't know, some number. I think I don't know. There's somewhere I've got a number. I think uh, might actually weigh half as much, but have the exact same inertia, mass times distance squared. So it's smaller, but what it does is it uses the principle that the farther you can get something away from the axis of rotation, um, the better you are. Well, that's why we have I-beams. We have nothing at the centroid of the eye, and we put it all out at the outside. So that was one of the reasons. So again, the analogy that we're going to use, the eye of the moment of inertia of an area, is the area that we have times distance squared.